All right, I want to put together a little bit of summary for second order systems and look at one last example that's underdamped. All right, so in step one here, we find the transient response by solving the homogeneous equation. All right, in the case of, that's always the case, but in the case of a second order, we get a second order quadratic equation, which we call our characteristic equation, which we need to solve. Okay, find its two roots and we'll get our two exponentials. They may be complex, that's okay. All right. Step two, we find the particular solution by guessing a steady state solution, or yp of t, that looks like the input, x of t. So if we have a constant input, we'll guess a constant output, or a constant y sub p. If we have a cosine input, we'll guess a cosine y sub p. All right. That's always important for us to remember. And then what we need to do is to find the unknowns in the total solution using the initial conditions. And I've written out what I had in the previous video, these kind of 4 sub-steps. So first thing we do is just write down the expression for the total solution. We put yc and yp together. All right, I've kept the general yp of t plus our general form here, c1 e to the s1t plus c2 e to the s2t. Now notice one thing this doesn't include is the critically damped case. But I almost never look at the critically damped case because I think it's ridiculous. It never really happens in the real world. It's really just a mathematical thing. All right. Most likely I'm going to give you undamped, underdamped, and overdamped. All right. So I can write the derivative. Then that's step 3b here, our little second sub-step. Right. I write the derivative expression down. So that involves taking the derivative of the particular solution and the derivative of the transient. The derivative of the transient is easy. It's just S1 is brought down in front and S2 is brought down in front. So then in my third substep here, I enter the initial conditions. So what I do is I have y of 0, and then what I wrote here is I plugged in. So notice what would have happened. Y of 0 equals yp of 0 plus c1 e to the 0 plus c2 e to the 0, right? So the e to the zeros would have gone away. And I bring yp of 0 over to the other side, and I get that result, okay? I can do a similar thing with the derivative expression, and I get something like that, okay? Then what I do is I put all of that in matrix form, which is easy to do in MATLAB, okay? So over here, let's look at another example. All right, so in this case, what I have is the second order equation looks like this. I have y of 0 is equal to 3 and y prime of 0 is equal to 0. Okay, so we were given those two initial conditions. So step one, we need to find the transient response, which means we need to find the homogeneous equation. So in this case, d squared y sub c by dt squared plus 4 dyc by dt plus 9yc equals 0, right? The only thing different about this equation, I've set it equal to 0. Now we know that we should guess y sub c equal to c e to the st with c not equal to 0. And I jump down. Basically at this point, I can say, well, I could put that in there. I know it's just going to lead to the characteristic equation that I need to solve, s squared plus 4s plus 9 equal to 0. Now, let's quickly do the quadratic formula on this. S equals opposite of b, so minus 4, plus minus the square root of b squared, that's 16, minus 4ac, so that's 4 times 9, all over 2 times a, like that. So I can see right now 16 minus 4 times 9, that's 16 minus 36. That's going to be a negative number. So I'm taking the square root of a negative number, which means that I'm going to get a complex result, right? So I'm going to write this as negative 2 plus minus j omega d, where I know that the two roots I'm going to get are going to be complex conjugates of each other. And we wrote down here, let's go back to sort of our general forms of the solution. So this guy's clearly in the underdamped category, where I'm going to have a fully complex result and my two roots to be complex conjugates of each other, okay? that means in general, I have this y sub c. I basically have two complex exponentials. One's going to rotate in the positive direction. One's going to rotate in the negative direction, right? And ultimately, I can use Euler's identity to combine those two things into what I call a decaying cosine. And the decay is controlled by the e to the sigma t. Now, as I've said, because this is a real system, the real part of the roots must always be negative to enforce the decay rather than the growth, all right? Because in a real system, the transient better decay and not grow, okay? Now, if I want to figure out the exact values here, again, I could do the computation. I don't want to. I asked MATLAB to do it for me, right? So what I did was I took the characteristic equation s squared plus 4s plus 9 equals 0, and I took the coefficients of that and put them into a vector here, right? So I took the coefficients 1, 4, and 9 and put them as the coefficients in a row vector and used the roots command to find the two roots. Now, if you want to know more about the roots command, you can type help roots, all right, in MATLAB, or you can just Google MATLAB roots command and you can find examples and a help page, okay? So what you see by saying s equals roots, I get this sort of vector result here where I see that I have s of 1 is equal to -2 plus j times 2.2361. This guy, the imaginary part, is going to be called omega d, all right? And then s of 2, this is what I've called s1, right? S of 2 is what I've called s2, and that's obviously going to be the complex conjugate of this guy, so minus j omega d. Okay, so omega d is the imaginary part of that. Okay, all right. So at this point, I guess I know sort of what my result is, but I'm not, I know it's going to be a decaying cosine, but I'm not going to go that far yet. I'm just going to say that this guy is yc of t equal to c1 e to the s1t plus c2 e to the s2t, like so. And I'm just going to leave it at that, okay? Now, I'm going to jump forward now. Again, before I go any further, I don't know enough yet to figure out C1 and C2. Remember, we can't figure those out until we have the total solution in step 3. Okay, so we got to hold off for a moment. All right, so I got to guess a YP. So let's write down what our expression is. So we had d squared y by dt squared plus 4 dy by dt plus 9y equals u of t. Okay, so I have a unit step as my input. So I'm going to say that my output is going to be a constant multiplied by a unit step, because if I have a constant in, I'm going to have a constant out. Okay, so what I'm going to do is I'm going to write this for t greater than or equal to 0 only and get rid of the u of t. And I'm going to say I have d squared by dt squared of b, a constant, plus 4 times the derivative of a constant, plus 9 times the constant is equal to 1. Now, you guys know right off the bat, right, that the derivative of a constant is 0, and so the second derivative of it must also be 0, and I have 9b equals 1, or b equals 1/9, right? Which tells me that yp of t is equal to 1/9 u of t. So my steady state solution is the number 1/9, all right? And of course, that's only for t greater than or equal to 0. Okay, so let's move on. All right, so we know what our particular solution is. We know the form of our transient solution, but we don't know C1 and C2. So we're going to go through those 4 sub-steps here to get C1 and C2. Okay, so I say the total solution is equal to yp, so that's 1/9, times c plus c1 e to the s1t plus c2 e to the s2t for t greater than or equal to 0, so I can get rid of the u of t's. Okay, And the thing I'm going to do is I'm going to leave it in this very general form right now, because I like leaving it in the general form because ultimately that makes it a little bit easier to write out equations in MATLAB. Okay, and I like that. Now I want to take the derivative of that general result because I'm going to need the derivative to get C1 and C2. All right, so the derivative of the particular solution is 0. All right. And then the derivative of C1 e to the S1t is going to be plus S1 e to the S1t, times C1 e to the S1t. And I get a similar result when I take the derivative of the other term, S2 C2 e to the S2t. And this is only true for t greater than or equal to 0. Okay. All right. So now I want to get to my third substep here, which is to plug in the initial conditions. So the two initial conditions that I was given, at the beginning of the problem were that y of 0 was equal to 3 and that the first derivative evaluated at 0 was equal to 0. So what I'm going to do now is I'm going to go and I'm going to plug those results into these two expressions. So for y of t, I have 1/9, right, plus C1 e to the 0 plus C2 e to the 0. Okay. Again, even if those exponents S1 and S2 are complex, doesn't matter. Complex number times 0 is still 0. Okay. The derivative we said previously was 0. And we had S1 C1 e to the 0 plus S2 C2 e to the 0, where I plugged t equal to 0 into these two terms. And I get that. Of course, we know e to the 0 is always equal to 1. So I can just get rid of those like that. And I see that I've got a system of equations now that I'm going to write like this. C1 plus C2 equals 3 minus 1/9. And S1 C1 plus S2 C2 equals 0. So I can write that as a system of equations C1, C2, S1, S2. Oops, that's not the way I want to write this. Right? I want to say 1, 1, S1, S2 times C1, C2 equal to 3 minus 1/9 and 0, like that. All right, so I'm going to call, so if you're not familiar with this, again, matrix form, 1 times C1 plus 1 times C2 equals 3 minus 1/9. I take the first row of this expression times this column, the second row of this matrix times this column. All right, so in matrix form, I'm going to say this is the matrix A, this is the matrix C, and this is B. Okay. So if I want to solve for C, I say C equals A inverse times B. All right, which in MATLAB speak is INV, that's inverse, times B, like that. Okay. All right. And that is our result. All right. So here's how we go about this. I wrote code to do this. So here's my roots expression. All right. And then I said y of 0. I defined that as a variable y underscore 0. I said that was equal to 3. And y underscore prime underscore 0. This guy is my y prime of 0. This guy is my y of 0. I defined variables like that. And then I created the b vector, right? So you can go back and you can look at the math on the previous slide and you can see that this math is correct. And I have a semicolon here because I want y0 minus 1/9 to be in the first row. And I want y prime 0 minus 0 to be in the second row. So I need a semicolon if I want them to be in different rows. Similarly with the A matrix here, I have 1, 1, and then I have a semicolon to make sure that S of 1 and S of 2 are on the next row. Now I say S of 1 and S of 2 because remember, if I look at the S here S is equal to a vector that has the two roots in it. And if you look at them, S of 1 is equal to S1 and S of 2 is equal to S2. We already talked about that. Okay, you can go back and look if you're not sure. All right, so then I solve for C by saying it's the inverse of A times B, and I get these two complex results, which are in fact complex conjugates as we suggested they were, okay? So the first entry of that, C of 1, is my C1, and the second entry of that is my C2, okay? So I'm going to use that later on. Because they're complex conjugates, so what I did down below is I took the absolute value, so that gives you the magnitude, and I took the angle, right? The angle function comes out in radians. I like it in degrees, so I multiply by 180 over pi. So I see the magnitudes are the same, but the angles are the opposites, which is not surprising, right? Because they're complex conjugates. So the way I'm going to write this is I'm going to say C1 has a magnitude of C1 and it has an angle C1. And because C2 is the complex conjugate, I could write it a similar way in terms of the magnitude of C2 and the angle of C2. But I'm going to say it has the same magnitude as C1 because it does. And I'm going to say its angle is the negative of the angle of C1. All right, I'm going to use that here in a second. All right, now let's get to what the total solution is, which is going to be ultimately, I'm going to start out with it in this form, right? I know what C1 and C2 are now. I know what S1 and S2 are now. So now I can basically get an expression with numbers. All right, now that ultimately is going to become what I have here, right? This decaying cosine. And I want to show that it becomes this decaying cosine. All right, so let's take this expression here. And let's specifically look for t greater than or equal to 0. That guy is going to be equal to 1/9 plus, now I'm going to plug in for C1, that it's the magnitude of C1, e to the j angle C1. So I plugged in, this is C1, times e to the negative 2t e to the j omega d t. This guy here is my S1, because remember S1 equals negative 2 plus j omega d, and S2 equals negative 2 minus j omega d. And you should see that if I have e to the a plus b, that's going to become e to the a times e to the b. That's exactly what I've got there. All right. So this is more explicitly, I should say, this term here is e to the S1t. And then I say I have magnitude C. So for C2, C2 is magnitude C1 with a negative angle of C1 times e to the negative 2t times e to the negative j omega dt, like that, okay? Where this guy is my e to the S2t. And you can see how that breaks up again if you plug in the roots. All right, so we're plugging right along now. What I'm going to do is I'm going to try to simplify this a little bit. I'm going to say I have 1/9 plus magnitude C1, and I see I have an e to the negative 2t in both terms and a C1 in both terms. So I'm going to factor out a C1 or magnitude C1 and e to the negative 2t, and see that I'm left with e to the j angle. So I'm going to write it like this. I'm going to group these two terms, e to the j omega dt plus angle C1, like that, plus e to the negative j omega dt plus angle C1, like so. All right. Now that looks like, and you should be able to see how these two terms would combine to give you this. All right. Now I'm going to go back to the fact that cosine of theta equals 1/2 times e to the j theta plus e to the minus j theta, like so. right? In this case, it looks like in this expression here, it looks like I could say I have theta equal to omega dt plus angle C1, right? Now, if you do that, now you notice it looks pretty similar, except for the fact that I don't have that 1/2. What it looks like I have is just simply 1 times e to the j theta plus e to the minus j theta. Well, what happens if I multiply both sides of this expression by 2, right? If I multiply the left side by 2, then I multiply the right side by 2, and this guy becomes just 1, okay? So knowing that, it looks like I could rewrite this as 1/9 plus 2 magnitude C1 times e to the negative 2t times cosine of omega dt plus angle C1. All right, nice and simple and clean. Now, that's my total solution at this point. All right, and I don't want to put numbers in for C1 and angle C1 and omega d because they're just messy. Here's how I plot that. So somewhere above, I entered what omega d was. Okay. Then I created a time vector, which in this case, I've said that goes from t underscore d over 1,000. These are the increments. And it goes from 0 to for 3 periods of that decaying cosine. Okay. Now, seeing the periods isn't always all that obvious in this particular case because of the fact that it's decaying, right? So it's hard to see the periods, but they're there. Okay. And if I look at this, all right, here's the expression in my code, right? So what I have is 2 times C mag. Now, C mag somehow must be a variable that I created, which somehow used the absolute value of C of 1, let's say, right? So use the absolute value of that particular value, because remember, C had 2 numbers in it, right? It had C of 1 and C of 2. It was set up as a matrix, okay? Specifically as a column vector is what I would call that. So C of 1 corresponded to what I've been calling C underscore 1. So I put in 2 times the magnitude of that guy. And then what I did here is I said times the exponential of the real part of S of 1 times t, okay? Now notice my parentheses are a little bit funny here, right? I probably should have done real part like that, all right? But that's okay. I took the real part of S1 times t. That's okay, because if you look at the real part of S of 1, it's negative 2. So what I've really written there, if you think about it, is real of negative 2 plus j omega d, right? This is my S of 1 times t, right? The real part of that is going to be negative 2t, all right? Because time is never going to be a complex number. Time's always going to be a real number. So I know that the real part of this is always going to be e to the negative 2t. So this guy here is simply e to the negative 2t, okay? And then I have my cosine omega dt, and I called phi the angle of C in this, or angle of C1. So in this case, phi is equal to the angle of C of 1. Now, because that comes out in radians, I usually multiply it by 180 over pi. And when I put that into the cosine function, which always expects to have a input in radians, I multiply by pi over 180, okay? Now, one thing is I have the dot multiply here because I want to multiply each element in the exponential by each element in the cosine. Remember, those are each going to be row vectors. So if the exponential, let's say, had entries 1, 2, 3, and I said multiply that by 4, 5, 6, that operation does not work as a matrix operation. I would say the first row here by the first column here, I can't do that. I would need 3 entries in each of these columns here. Or so I'd need 2 entries underneath the 4 to make that work. So MATLAB's going to bark at you. But that's not what you intended, right? What you intended was for the result to be 1 times 4, and the next entry to be 2 times 5, and the next entry to be 3 times 6. If I want to multiply each element like that, we said we do a dot multiply. Now notice I don't have a dot multiply on every multiplication. I only have it where I'm multiplying those two vectors. Now, if you have extra dot multiplies, it doesn't really matter. I just don't need them. Okay. All right. Then I created my particular solution using the ones command, and I made it the same size as my time vector. And then I combined yp and yc. And here's what it looks like. So clearly, this guy is yp, the blue line. And a little trickier to see, but I can see my transient goes to 0 here. So this guy is y sub c. And this yellowy guy here is y, the sum of them. Now again, as I've said before, y sub c doesn't exist in the real world by itself. Y sub p doesn't exist in the real world by itself. The total solution always does. All right. And what I find is that by the time I get out here, where the transient is basically decayed to 0, y sub p and y have become basically the same once I get out here, right? So in this range, I guess I'll do it this way. Out here, I have that y is approximately y sub p in that range. Okay, that should always be the case. Now, check for me, right, is if I look at the initial value here, y of 0 does look like it's 3. That's what I had said it was supposed to be. And I think the initial condition on the derivative was that it was equal to 0. And if I zoomed in here, I would see this guy is basically flat up there at the top, right? Which tells me that the initial condition on the derivative is 0. If he's flat, that would lead to a 0 derivative there.